Module 28, Lecture A, Hyperparameter Search. By the end of this lecture, you will be able to construct parameter grids and distributions for pipeline hyperparameters, run exhaustive, randomized, and successive-halving searches, and interpret search results and refit the best model using single or multiple metrics. Search spaces. Parameter grid basics. A parameter grid defines the hyperparameter choices that a model selection process will test across a machine learning pipeline. These choices can apply to pre-processing steps, such as scaling or encoding, as well as to the final model, such as its regularization strength. By setting this search space in advance, the pipeline can systematically compare alternatives using methods like cross-validation. When setting pipeline hyperparameters, name each one by both its pipeline step and the specific setting it controls. This avoids confusion when different steps have similar options, such as feature extraction and classification in a text classification workflow. A clear parameter grid makes it easier to compare configurations, reproduce experiments, explain results, and audit the process. An effective parameter grid should be broad enough to test meaningful alternatives, but focused enough to avoid wasting computation on minor variations. Use domain knowledge and past results to choose a small set of important values for each hyperparameter, such as regularization strength, pre-processing choices, missing data handling, scaling, or model complexity. The grid should match the logic of the pipeline because it defines which experimental questions the search can answer. Python code. Parameter grid basics. Create a small parameter grid for a pipeline, making clear that each hyperparameter is prefixed by the name of its pipeline step. Before running any search, count how many parameter combinations the grid will produce. We import key Scikit-Learn tools for building a simple machine learning workflow. The Iris dataset loader provides sample flower data, while the parameter grid supports hyperparameter tuning. A pipeline connects pre-processing and modeling steps, using a StandardScaler to normalize features before applying logistic regression as the classification model. We load the Iris dataset using Scikit-Learn's load_iris function, a common choice for small demonstrations and tests. Then, we check that the number of feature rows matches the number of target labels. If they do not match, an error is raised, because supervised learning requires every feature vector to have a corresponding label. This pipeline combines two key steps into one workflow. First, it standardizes the features using a StandardScaler, and then it trains a logistic regression model. The logistic regression is allowed up to 200 iterations to converge. This makes pre-processing and modeling more streamlined and consistent. This section defines a parameter grid for tuning a machine learning pipeline, with each hyperparameter tied to its pipeline step to avoid confusion. The scaling step tests whether the data should be centered or not, while the logistic regression model tests three regularization strengths, 0.1, 1, and 10. The model uses the LBFGS solver, creating a clear setup for comparing hyperparameter combinations during tuning. The parameter grid is expanded into all possible parameter combinations using Scikit-Learn's parameter grid tool. The result is then checked to confirm that it contains exactly 6 combinations. If it does not, an error is raised to signal that the grid was not set up as expected. We first check the Scikit-Learn version to support compatibility and reproducibility. Then, we inspect the pipeline steps, the hyperparameters being tuned, and the total number of grid combinations. Finally, viewing the first and last configurations gives a quick sanity check that the tuning grid is set up as expected. This script shows how to define a parameter grid for a scikit-learn machine learning pipeline using the iris dataset. The pipeline scales the data and then applies logistic regression, while the grid tests options for centering during scaling and different regularization strengths. Expanding the grid produces 6 possible configurations, helping illustrate how hyperparameter settings can be explored systematically. Grid search. Grid search tests every specified combination of hyperparameters to find effective model settings. You choose the options to compare, such as feature choices or regularization strength, and the search evaluates them systematically. It is simple, transparent, and useful when the number of possible configurations is manageable. A good hyperparameter grid should reflect realistic modeling choices and task constraints, not random or exhaustive values. For example, it may compare simpler and more complex decision trees, or different regularization strengths for support vector machines based on data noise. In pipelines, grid search can also tune pre-processing choices, such as imputation or scaling, alongside the model. The goal is to test meaningful options that are likely to affect performance. Grid search becomes costly as more hyperparameters and values are added, especially with cross-validation, large datasets, or slow models. A practical approach is to begin with a broad, simple grid, then narrow the search around promising settings. Since grid search only tests the values you choose, it works best when guided by domain knowledge or earlier experiments. Python code, grid search. This example demonstrates a small grid search, where pipeline parameter names link each step to its settings. The results show which combinations were tested and identify the best settings. This setup imports the main scikit-learn tools needed for a classification workflow. It loads the breast cancer dataset, splits the data into training and testing sets, and uses a pipeline to organize pre-processing and modeling. The features are standardized with a StandardScaler, logistic regression is used as the classifier, and grid search is included to test different model settings. We load the breast cancer dataset from Scikit-Learn for a classification task, then separate it into input features and target labels. The features are the data used to train and test the model, while the labels are the outcomes the model learns to predict. This provides the basic supervised learning setup of paired inputs and correct answers. Before modeling, the code verifies that the feature data and target labels have the same number of rows. This confirms that each example has a matching label, which is required for supervised learning. If the counts do not match, it raises an error, so the data can be fixed before training continues. We split the data into training and testing sets, so the model can be evaluated on examples it has not seen before. A quarter of the data is kept for testing, while stratification preserves the same class balance in both sets. A fixed random state makes the split reproducible. This pipeline combines preprocessing and modeling in one workflow. It first standardizes the features, so they have a mean of 0 and a standard deviation of 1. Then applies logistic regression as the classifier. The model is allowed up to 1,000 iterations to help it converge, and the pipeline makes later tasks like grid search easier to manage. This section defines a parameter grid for grid search using pipeline step names to identify which model settings to tune. For logistic regression, it tests different regularization strengths, uses L2 regularization, and selects the liblinear solver. This lets grid search compare parameter combinations and choose the best model configuration. Grid search with cross-validation tests each specified parameter combination for the model pipeline. Using 5 folds, it trains and validates the model on different splits of the data, measuring performance with accuracy. After the best settings are found, the model is refit on the full training set using those optimal parameters. The grid search fits the training data by testing each hyperparameter combination with cross-validation. It selects the settings that give the best accuracy, then refits the model on the full training set using those settings so it is ready to evaluate on new data. To review the grid search, first check the stored parameter results to see how many model configurations were tested. Then use the grid search scoring method on the test data to measure the accuracy of the best refit model. This output summarizes a grid search by first noting the Scikit-Learn version for reproducibility, then showing which hyperparameters were tested and how many combinations were evaluated. It reports the best parameter settings and the best cross-validation accuracy, rounded to 3 decimal places. Finally, it gives the test accuracy after refitting the model with those best settings, showing performance on unseen data. This script uses grid search to tune a logistic regression model on the breast cancer dataset. It builds a pipeline with standard scaling and logistic regression, then tests several regularization strengths using 5-fold cross-validation. After finding the best settings, it refits the model and reports key results, including the best parameters, cross-validation accuracy, and final test accuracy. Parameter distributions. Parameter distributions define a hyperparameter search space using ranges or probability patterns instead of fixed lists of values. They are useful when many values are possible or when a small grid may miss good settings, such as for regularization strength or learning rate. This makes model tuning more flexible by exploring a broader landscape of possible choices. Choose hyperparameter distributions based on the type and scale of each setting. Categorical choices, such as penalties or kernels, should come from defined options, while numerical values, such as learning rates, need ranges that reflect their possible effects on the model. Integer settings, like tree depth, should match their structural role. And in pipelines, each distribution must be assigned to the correct processing step. When resources are limited, parameter distributions help sample a practical set of hyperparameter configurations, while still covering many possibilities. These distributions must be chosen carefully, because unrealistic values can waste time and hurt model performance, such as overly deep trees or learning rates that are too large. Good distributions, guided by domain knowledge and past experiments, make hyperparameter search more efficient and effective. Python code, parameter distributions. This example samples hyperparameter distributions for a pipeline, using ranges rather than fixed grids. The result is a set of realistic candidate settings to evaluate. This setup imports the main tools needed for a machine learning workflow. NumPy and Pandas support numerical work and data handling, while Scikit-Learn provides tools for sampling hyperparameters, standardizing features, building a logistic regression classifier, and combining pre-processing with modeling in a pipeline. We build a simple machine learning pipeline with 2 parts, a StandardScaler to normalize the features, followed by logistic regression for binary classification. This setup makes pre-processing and modeling work together cleanly, while also giving each step clear parameter names that can be referenced and adjusted later. A parameter distribution dictionary defines the hyperparameter search space for the model pipeline, with each entry targeting a specific pipeline step and parameter. For logistic regression, it tests a wide range of regularization strengths from 10 to the power of -3 through 10 to the power of 2. It also fixes L2 regularization and the LBFGS solver, while trying several maximum iteration limits to help the solver converge. The code uses Scikit-Learn's parameter sampler to randomly choose 6 hyperparameter combinations from the given distributions. A fixed random state makes the results reproducible, while the sampled settings provide a varied but efficient way to explore the search space, without testing every possible option. The sampled hyperparameter settings are converted into a simple table-friendly format. Each setting is summarized with its regularization value rounded for readability, and its maximum iteration value kept as is. These formatted entries are collected into a list, making the results easier for beginners to read and compare. The code turns a list of sampled hyperparameter settings into a pandas data frame. This organizes the candidates into a clear table, making the values easier to inspect, compare, and present. The process checks that the sample table contains exactly 6 rows, confirming that the parameter sampler produced the expected 6 hyperparameter settings. If the count is different, it raises an error to signal the mismatch. This validation helps ensure the experiment uses the correct number of candidate configurations. The output explains how Scikit-Learn names pipeline parameters by linking each step name to its parameter name with a double underscore. It then shows the sorted hyperparameter keys being tuned, followed by 6 sampled candidate settings drawn from a broad range of values for C. The printed sample summarizes the chosen values for C and the maximum number of iterations, making the tuning setup easier to review. This script shows how to sample hyperparameter distributions for a Scikit-Learn pipeline with scaling and logistic regression. Instead of testing only fixed grid values, it defines ranges for settings such as regularization strength, penalty type, solver, and maximum iterations. A parameter sampler randomly selects 6 candidate combinations, helping explore the tuning space efficiently. The output confirms the sampled settings and illustrates why distributions can be more flexible than fixed grids for hyperparameter optimization. Search methods. Randomized search. Randomized search helps tune hyperparameters when testing every combination would be too costly. It samples a fixed number of settings from chosen ranges, giving broad coverage while keeping computation under control. This makes it useful for complex machine learning pipelines where time and hardware resources are limited. Randomized search explores hyperparameter settings more flexibly than grid search by sampling a wider range of possible values instead of only fixed points. This is especially useful for settings like learning rate or regularization strength, where good values are hard to predict. It can also spend effort more effectively when some hyperparameters matter more than others, helping find strong model settings with the same computational budget. Randomized search works best when you choose sampling ranges and distributions carefully, guided by domain knowledge and earlier experiments. Ranges that are too narrow may miss good options, while ranges that are too broad can waste computation. Because results depend on randomness, it can help to set a random seed and use more samples for large or sensitive searches. Each configuration is usually checked with cross-validation, and the best result can then be refined further. Python code. Randomized search. Randomized hyperparameter search tests a set of candidate settings drawn from chosen distributions. Each candidate is evaluated with cross-validation, and the scores are compared to identify the most promising configuration. We import the main tools needed to build a simple machine learning workflow: NumPy and Pandas for data handling, Scikit-Learn for modeling, and the built-in breast cancer dataset for classification. Logistic regression is used as the classifier, while randomized search helps tune its settings. A pipeline combines feature standardization with model training, so the data is scaled properly before fitting. We load Scikit-Learn's breast cancer dataset as a ready-made example for classification. The data is separated into input features and target labels, which lets a machine learning model learn how the inputs relate to the correct outputs. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that every data point has a matching label. If they do not align, it raises an error to prevent incorrect training results or runtime failures. Use a scikit-learn pipeline to keep feature scaling inside cross-validation and prevent preprocessing from being separated from model training. The pipeline first applies standard scaling, so features have mean 0 and standard deviation 1. Then fits a logistic regression model with enough iterations to converge. This combines preprocessing and modeling into one efficient, consistent workflow. We set up the randomized search by defining key logistic regression options. The regularization strength is sampled across 50 values, from 10 to the -3 up to 10 squared, giving the search a broad range to test. We also allow 2 solver choices, liblinear and LBFGS, so the search can identify which optimization method works better for the data. We use Scikit-Learn's randomized search to tune a pipeline with scaling and logistic regression. It samples 8 combinations of regularization strength and solver type, evaluates them with 5-fold cross-validation, and selects the best option based on accuracy. A fixed random state makes the results reproducible. We fit the search object to the dataset to run randomized hyperparameter tuning with cross-validation. After the search finishes, we store the results in a pandas data frame so we can compare how each tested parameter combination performed. Create a simplified data frame from the cross-validation search results, keeping only the key details: the C hyperparameter, the solver, and the mean test score. Round the mean test score to 3 decimal places, so the results are easier to read and compare. This makes it simpler to see which parameter settings performed best. The code ranks the summary results by average test score, so the strongest hyperparameter settings appear first. It then keeps the top 5 candidates and renames key columns to simpler labels, making the results easier to read and interpret. The code reports key results from a randomized search for model tuning. It shows the scikit-learn version, how many parameter settings were tested, the best cross-validation accuracy, and the parameter values that achieved it. It also summarizes the top-performing settings, making it easier to compare which combinations worked best. This script uses randomized search to tune a logistic regression model on the breast cancer dataset. It builds a pipeline that standardizes the features, then tests random combinations of regularization strength and solver type using 5-fold cross-validation. The model is scored by accuracy, and the script reports the best score, the best settings, and a brief summary of the top 5 configurations. HalvingGridSearch. HalvingGridSearch is a more efficient alternative to exhaustive grid search when testing every hyperparameter combination fully would be too expensive. It begins by evaluating many candidates with limited resources, then repeatedly removes weaker options and gives more resources to the stronger ones. This lets the search focus on the most promising combinations while avoiding the cost of fully testing the entire grid. HalvingGridSearch saves computation by testing many model settings with limited resources at first, such as fewer training examples or iterations. Weak candidates are removed early, and only the stronger ones receive more data or training for further evaluation. This makes it especially useful for large datasets or models that take a long time to train. HalvingGridSearch can save time by giving more resources to the most promising model settings. But early results can be misleading. A model may look weak with little data and improve later, or look strong at first and decline with a larger budget. Search quality depends on choosing the resource, starting budget, and elimination rate carefully, so useful options are not removed too soon. Python code Halving Grid Search. This demonstration shows halving grid search for classification. Candidate models are tested in rounds with increasing training resources, while weaker options are removed along the way. The results summarize each round, the surviving candidates, and their accuracy. This setup imports the main Scikit-Learn tools needed to build and evaluate a classification model. It loads the breast cancer dataset, prepares logistic regression as the classifier, and uses accuracy to measure performance. The workflow also includes splitting the data into training and test sets, standardizing features with a scaler, and organizing the steps in a pipeline. For hyperparameter tuning, it enables and imports HalvingGridSearch cross-validation, which efficiently narrows many candidate settings down to the best options. We load Scikit-Learn's built-in breast cancer dataset for a quick classification example. The dataset is separated into features and target labels, which prepares it for training and evaluating a machine learning model. Before training, the code verifies that the feature data and target labels have the same number of entries. This ensures every data point has a matching label. If they do not align, it raises an error to prevent problems during model training and evaluation. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 1/4 of the data kept for testing. This lets the model be evaluated on data it did not see during training. Stratification preserves the class balance in both sets, and a fixed random state makes the split reproducible. A pipeline combines feature scaling with logistic regression, so preprocessing happens correctly inside cross-validation. The scaler standardizes features to have zero mean and unit variance, which helps scale sensitive models like logistic regression. Setting a higher iteration limit gives the model enough time to converge, while the pipeline ensures the same scaling process is applied consistently across every fold. We set up a hyperparameter grid for the logistic regression pipeline, testing different regularization strengths from 0.01 to 10 and 2 optimization solvers, liblinear and LBFGS. This lets the HalvingGridSearch compare combinations and choose the model that performs best. We use Scikit-Learn's HalvingGridSearch to tune a pipeline with scaling and logistic regression. It tests many hyperparameter combinations at first, then gives more resources only to the better performers, keeping about half each round. Performance is measured with threefold cross-validation. Accuracy is the target score, and a fixed random state makes the results reproducible. The HalvingGridSearch fits the model to the training data while testing different hyperparameter combinations with cross-validation. It starts with many candidates, then gradually keeps only the strongest ones and gives them more resources in later rounds. This efficient process identifies the settings that achieve the best training accuracy and selects the best model configuration. The trained search object uses its best pipeline from the HalvingGridSearch to predict labels for the test data. The predictions are then compared with the true test labels to calculate accuracy. This score gives a final measure of how well the selected model performs on unseen data. This step summarizes the HalvingGridSearch by identifying the unique iteration rounds, reporting the Scikit-Learn version, and calculating the total number of grid candidates from the tested values of C and the 2 solvers. It then reports how many halving rounds were actually run, giving a quick view of the search scale and supporting reproducibility. The loop reviews each unique round from the search results and counts how many candidates were evaluated in that round. It does this by matching entries to the current round number, then prints the round and its candidate count. This provides a concise summary of the halving process and how many candidates remained at each stage. After the HalvingGridSearch, we report the best hyperparameters to show which settings worked best for the model. We then give the best cross-validation accuracy and the final test accuracy, both rounded to 3 decimal places. Together, these results summarize how well the model is tuned and how effectively it performs on unseen data. This script uses HalvingGridSearch to tune a logistic regression model on the breast cancer dataset. It keeps the test set separate, standardizes the training data, and searches over regularization strength and solver choices. The search starts with many hyperparameter candidates, then keeps only the stronger ones as it evaluates them with more data. It reports the candidates tested in each round, the best settings, cross-validation accuracy, and final test accuracy, showing how HalvingSearch finds good hyperparameters efficiently. HalvingRandomizedSearch. HalvingRandomizedSearch tunes hyperparameters by testing many random settings with a small resource budget, then keeping only the strongest candidates for further evaluation. In each round, weaker options are discarded, and the remaining ones receive more resources. This reduces the number of candidates over time, so the method can explore large search spaces without fully training every model. It efficiently balances broad exploration with focused improvement. HalvingRandomizedSearch is an efficient way to tune models when the hyperparameter space is large or training is expensive. Instead of testing every combination or giving all random candidates the same resources, it starts many candidates with a small budget, drops weaker ones early, and spends more effort on the most promising options. This helps find strong models within practical time and computing limits. HalvingRandomizedSearch can tune machine learning models efficiently, but its results need careful interpretation. Early performance may not always predict final performance, because some models improve with more training while others plateau. Its success depends on sensible resource budgets and elimination choices, and different randomized runs can produce different outcomes. Used thoughtfully, it balances trying many options with focusing on the most promising ones. Python code, HalvingRandomizedSearch. This script shows having randomized hyperparameter search, where weaker candidates receive less training data early on. Across rounds, the output demonstrates how poor candidates are gradually removed while stronger ones continue. This setup imports the main Scikit-Learn tools needed to build and tune a classification model. It loads the breast cancer dataset, prepares training and testing splits, and creates a pipeline that standardizes the features before applying logistic regression. It also enables and imports HalvingRandomizedSearch, which efficiently tunes hyperparameters by narrowing down the best candidates over time. We load Scikit-Learn's breast cancer dataset for a classification task and separate it into input features and target labels. The features contain the data used for modeling, while the target labels provide the classes the model will learn to predict. Before training, the code verifies that the feature data and target labels have the same number of entries. This ensures every feature set has a matching label. If they do not align, it raises an error to prevent problems during model training. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 25% reserved for testing. This lets the model be evaluated on unseen data for a more reliable accuracy estimate. Stratification keeps the class balance the same in both sets, and a fixed random state makes the split reproducible. The workflow uses a pipeline to combine preprocessing and modeling in one sequence. First, the data is standardized, so each feature has a mean of 0 and a standard deviation of 1. Then, logistic regression is applied for classification, with enough iterations allowed for the model to converge. This makes the machine learning process more efficient and easier to manage. The hyperparameter settings define what the randomized search will try for a logistic regression model. It explores different regularization strengths from 0.01 to 100, uses L2 regularization, and applies the LBFGS solver. Together, these choices guide the tuning process towards suitable model settings. We set up a HalvingRandomSearchCV to tune a pipeline with scaling and logistic regression. The search starts with 12 hyperparameter combinations, evaluates them using threefold cross-validation and accuracy, then repeatedly keeps the stronger candidates while giving them more training samples. A factor of 2 means the number of candidates is halved each round, as the data used is doubled. A fixed random state makes the results reproducible. The model is fit on the training data using a HalvingRandomSearchCV. This search automatically performs cross-validation to compare different hyperparameter settings. After fitting, the cross-validation results are saved and can be used to review how each tested setting performed. The code gathers the unique iteration numbers from the cross-validation results to identify each round of the halving search, then sorts them in order. It also prints the Scikit-Learn version, which helps with reproducibility and checking feature compatibility. For each unique round, the results are filtered to find the candidates in that round. The count of matching candidates gives the numbers still active, and the shared resource value for that round shows how many samples or resources were used. Printing these values summarizes how candidate elimination progresses from round to round. We evaluate the selected model on unseen test data using the search object's scoring method, which reports its accuracy. We then show the best value of C, the logistic regression regularization setting, and the test accuracy rounded to 3 decimal places. Together, these results summarize how well the tuned model generalizes to new data. This script uses HalvingRandomSearchCV to tune a logistic regression model on the breast cancer dataset. It builds a pipeline with scaling and logistic regression, then tests many regularization settings while gradually removing weaker candidates. Each round evaluates fewer candidates with more training data, focusing computation on the most promising options. The script reports the search progress, then gives the best regularization value and the model's test accuracy. Interpreting search results. Resource settings. Resource settings control how much computation a hyperparameter search can use. In grid and randomized searches, cost grows with the number of candidate settings and cross-validation splits, since each model must be trained and evaluated. Successive-halving saves effort by giving many candidates few resources at first, then increasing resources only for the most promising ones. When interpreting results, consider whether performance reflects a truly better setting, extra resources, or too little training to reveal a model's potential. When reviewing a resource-aware search, compare candidates at resource levels that are meaningful for the task. Early results can help remove weak options, but they may be unreliable because some models need more resources to show their true performance. For example, neural networks may improve after more training, and random forests may stabilize as more trees are added. This is especially important in areas like fraud detection or medical imaging, where choosing a fast but weaker model can lead to poor outcomes. Resource settings control the trade-off between faster experimentation and more reliable model selection. Larger budgets improve confidence, but require more time and computation, while smaller budgets can make results less dependable. After choosing the best hyperparameters, retrain the model on the full dataset, so the final model is not limited by the resources used during the search. Python code. Resource settings. This example compares resource levels in HalvingSearch, where the resource is the number of training examples used for each candidate. It highlights how performance changes as more data is allocated, and shows why refitting the final selected model is important. This setup imports the main tools needed to build and tune a machine learning classifier. NumPy and Pandas support data handling, while Scikit-Learn provides the breast cancer dataset, logistic regression model, train test splitting, pipelines, and feature scaling. It also enables HalvingGridSearch cross-validation, which tunes hyperparameters efficiently by giving more resources to the most promising model settings. We load Scikit-Learn's breast cancer dataset for a classification task. The dataset provides both feature values and target labels, which are separated to prepare the data for modeling and analysis. Before modeling, the code verifies that the feature data and target labels have the same number of rows. This confirms that every data point has a matching label, which is required for supervised learning. If they do not match, it raises an error to prevent problems during training and evaluation. The dataset is divided into training and test sets, so the model can be evaluated on data it has not seen during training. A quarter of the data is reserved for testing, with stratification used to keep the target label proportions representative. A fixed random state makes the split reproducible. A pipeline combines pre-processing and modeling into one manageable workflow. It first standardizes the features so they have a mean of 0 and a standard deviation of 1, which helps logistic regression handle scaled data properly. The pipeline then applies logistic regression with enough iterations to support convergence. This setup makes the full process easier to manage and tune when searching for better hyperparameters. A grid of regularization strengths is defined for the logistic regression model, and a HalvingGridSearch is used to find the best setting within the existing pipeline. The search evaluates candidates with threefold cross-validation, using accuracy as the scoring metric. It gradually increases the number of training samples for stronger candidates, doubling the sample size each round. A fixed random state makes the results reproducible, and the best model is refitted on the full training data. The code starts a HalvingGridSearch to find the best model settings. It tests several candidate models on smaller portions of the training data, then gives more data to the most promising ones as the search continues. Using accuracy as the scoring measure, it efficiently selects the hyperparameters that perform best. Convert the cross-validation search results into a Pandas data frame so they can be analyzed easily. Then keep only the rows from the final HalvingSearch iteration. Copy that subset and sort it by test score rank. The top 3 entries show the best performing model candidates at the final resource level. The output reports the Scikit-Learn version for reproducibility, then shows the best regularization value selected by the HalvingGridSearch. After refitting the model with that setting, it prints the test accuracy to indicate how well the model performs on unseen data. The summary extracts the key cross-validation results: the regularization setting, the amount of training data used, and the average test accuracy. These columns are renamed for clarity. The accuracy is rounded to 3 decimal places, and the result is printed without row numbers. This gives a concise view of how the top candidates performed and how much training data they used. This script uses HalvingGridSearch to tune the regularization strength of a logistic regression model on the breast cancer dataset. It builds a pipeline with standard scaling, evaluates candidate settings with cross-validation, and gradually gives more training samples to the most promising options. After fitting, it reports the Scikit-Learn version, the best regularization value, the refitted model's test accuracy, and a brief summary of the top final candidates. The example emphasizes that final refitting is an important part of reliable model selection. Multi-metric refit. When a hyperparameter search uses multiple metrics, the best model is not always obvious because each metric reflects a different priority. Accuracy, precision, and recall can reveal important trade-offs, such as avoiding false alarms or catching more true cases. Multi-metric evaluation helps choose a model that fits practical, ethical, and stakeholder needs rather than optimizing only one score. In a multi-metric search, refitting means choosing which hyperparameter setting will be trained again on the full dataset after cross-validation. Cross-validation measures each setting on several metrics, but the final model is newly trained using the selected setting, not taken from a validation fold. With one metric, the choice is simple. With multiple metrics, you need a rule for the final decision, such as prioritizing F1 score or choosing a simpler model that still meets a recall goal. In a multi-metric refit, the chosen model reflects the selected refit priority, not necessarily the best score on every metric. A model may be picked for higher recall, even if others have better precision or overall ranking. So analysts should review the trade-offs among leading options. The goal is to align hyperparameter tuning with real-world priorities, such as finding more churn risks or balancing performance with fairness in loan decisions. Python code, multi-metric refit. This example shows how multi-metric refit can lead different evaluation metrics to select different models. The results highlight the trade-off between those metric choices. We import key Scikit-Learn tools for building and evaluating a classification model. These include the breast cancer dataset, logistic regression, precision and recall metrics, and a custom scorer. We also use grid search and train test splitting for model selection, plus a pipeline with standard scaling to combine pre-processing and modeling in a clean workflow. We load Scikit-Learn's breast cancer dataset, a built-in dataset for classification tasks. The data is then separated into input features and target labels, which identify each sample's class. This prepares the dataset for later processing and model training. Before training, the code verifies that the feature data and target labels have the same number of entries. This confirms that every data point has a matching label. If they do not match, it raises an error to prevent incorrect model training. The dataset is split into training and testing sets, so the model learns from one portion and is evaluated on separate data. The split keeps the target class proportions the same in both sets, which helps maintain balance for classification. 25% of the data is used for testing and 75% for training, with a fixed random setting to make the split reproducible. We use a pipeline to combine pre-processing and modeling in a consistent workflow. The features are first standardized to have a mean of 0 and a standard deviation of 1, which helps logistic regression perform properly. The pipeline then trains a logistic regression model with enough iterations to support convergence across different parameter settings. A parameter grid is used to test several regularization strengths for a logistic regression model. By trying values from 0.01 to 10, the grid search can compare how regularization affects performance and choose the setting that best balances training fit with generalization. We set up model evaluation to measure both precision and recall. A scoring dictionary stores scorer objects created from the precision score and recall score functions, so these metrics can be applied consistently during evaluation. This lets us compare how well each model performs on both measures. We use grid search with cross-validation to choose the best pipeline, combining scaling with logistic regression. It tests different regularization strengths and evaluates performance using precision and recall, but selects the final model based on the highest recall. With five-fold cross-validation, the search fits the training data and identifies the configuration that best meets the recall goal. We use the grid search cross-validation results to compare the evaluated model candidates. For each regularization value, we collect its mean precision and mean recall scores, creating a compact summary of performance across both metrics. We identify the result row with the best precision by comparing rows using their precision score, then repeat the process to find the best recall score. This shows which model settings perform best for each metric and helps reveal the trade-off between precision and recall. The output first confirms the Scikit-Learn version for reproducibility, then shows that model selection was refit using recall as the priority metric. It reports the best regularization setting for recall, compares it with the setting that gave the best precision, and highlights the trade-off between the two. Finally, it evaluates the refitted model on unseen test data by reporting its recall score. This example shows how Scikit-Learn can compare models using more than one metric, then choose the final model based on a selected metric. Using the breast cancer dataset, it trains a scaled logistic regression model with different regularization strengths and evaluates both precision and recall. The search refits the model using the setting with the best recall, then reports the related scores and test recall. The main point is that optimizing for precision or recall can lead to different model choices. So the refit metric should match the goal of the task. Reading CV results. Cross-validation results should be used to judge more than which model ranks highest. The mean validation score shows how well each setup performs on held-out data, but the variation across folds shows how reliable that performance is. A model with a slightly lower average score may be preferable if it performs more consistently, especially in critical settings like medical screening. Comparing training and validation scores shows whether a model generalizes well. High training performance with low validation performance suggests overfitting, while low scores on both suggest underfitting. If both scores are high and close together, the model is likely reliable. Training time also matters, because a small accuracy gain may not justify much higher computational cost. The top model in cross-validation is not automatically the best choice for real use. It is only the best among the models tested under the chosen scoring and validation setup. If top scores are close, or vary a lot across folds, several models may be effectively similar. So factors like simplicity and interpretability can guide the final choice. After selecting a model, it is usually refitted on the full training data before final testing or deployment. Python code. Reading CV results. When reviewing model search results, look beyond the single top score. Compare how stable validation performance is, whether models show signs of overfitting, and how quickly they run. After interpreting the results, refit the model you choose. This setup imports the main tools needed to build and evaluate a machine learning classifier. It uses NumPy and Pandas for data handling, Scikit-Learn to load the breast cancer dataset, split it into training and testing data, scale the features, tune hyperparameters, and organize the workflow in a pipeline. Logistic regression is then included as the classification model. We load Scikit-Learn's breast cancer dataset for a classification task, then separate it into input features and target labels. This prepares the data for later processing and model training. The code verifies that the feature data and target labels have the same number of entries, so every feature row has a matching label. If they do not align, it raises an error. This check helps prevent training or evaluation problems caused by mismatched data. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, while stratification preserves the class balance in both sets. A fixed random state makes the split reproducible, allowing the model to be trained on one portion of the data and evaluated on separate, unseen data. We build a machine learning pipeline that first standardizes the features, then trains a logistic regression model. Standardization gives features a mean of 0 and a standard deviation of 1, which helps logistic regression perform reliably. Keeping pre-processing and training together in one pipeline ensures the same scaling is applied during cross-validation, making model evaluation more consistent and trustworthy. A parameter grid is used to test several values for the logistic regression regularization strength, from very small to larger settings. A grid search then evaluates the full pipeline, including scaling and logistic regression, using 5-fold cross-validation. Accuracy is used to choose the best setting, and training scores are also saved, so performance on training and validation data can be compared for signs of overfitting. The model is trained on the training data using grid search cross-validation. This process tests different parameter combinations, evaluates them with cross-validation, and then refits the model using the best settings. The result is an optimized model configuration that can be used to make predictions on new data. We convert the grid search cross-validation results into a pandas data frame so they are easier to analyze. Then we focus on the key performance metrics: the regularization parameter C, the average test score, the variation in test scores, and the average training score. This summary helps compare how different C values affect model performance. Calculate each model's overfitting gap by subtracting its mean test score from its mean training score. Then sort the results by mean test score from highest to lowest, so the best performing configurations on validation data are easiest to identify. The code highlights the 4 best cross-validation results by mean test score, giving a quick view of the strongest hyperparameter settings. It rounds the values for readability, prints the Scikit-Learn version for reproducibility, and displays the key metrics cleanly, without row indices, including scores, variation, parameter values, and overfitting gaps. We evaluate the refitted model on unseen test data using the GridSearchCV scoring method, which reports test accuracy. We then note the best chosen value of the C hyperparameter and present the rounded test accuracy to show how well the model generalizes to new data. This script uses grid search to tune a logistic regression model on the breast cancer dataset. It splits the data into balanced training and test sets, applies standard scaling, and compares different regularization strengths with 5-fold cross-validation. The results help check both performance and possible overfitting by comparing training and validation scores. Finally, the best model is refit and evaluated on the untouched test set, reporting the chosen regularization setting and test accuracy. In this lecture, you learn to construct parameter grids and distributions for pipeline hyperparameters, run exhaustive, randomized, and successive-halving searches, and interpret search results and refit the best model using single or multiple metrics. In the next lecture, Lecture B, we will go over thresholds curves.
Thank you for your attention. See you all in the next lecture.